Tonight, we're looking at one of the biggest pressure points in the electric car world: how to make an EV that's meaningfully cheaper without making it feel like a compromise, and how Tesla's rumored 2026 compact, widely nicknamed the Model 2, could do exactly that through design choices that cut costs both outside and inside the vehicle. To be clear, Tesla has not officially launched a vehicle called Model 2, and it has not confirmed final specs, pricing, or styling for a 2026 compact. But Tesla has repeatedly pointed to a next-generation platform and a next-generation manufacturing approach aimed at dramatically lowering production cost. And that gives us enough signals to report on the core idea. The savings are likely to come less from one magic breakthrough and more from dozens of design decisions that reduce parts, reduce weight, reduce factory steps, and reduce complexity, while keeping the technology feel that buyers now expect. Start with the outside, because that's where cost-cutting can be hidden in plain sight. The simplest way to make a cheaper car is to make a smaller car. A compact footprint means less steel or aluminum, less glass, smaller wheels and tires, smaller brakes, and generally lower shipping weight. But the biggest outside benefit isn't just the body panels, it's what a smaller, lighter, more efficient shape allows Tesla to do with the battery. If you can reduce energy consumption per mile through size and aerodynamics, you may be able to hit a competitive range target with fewer kilowatt hours. And every kilowatt hour you don't have to build is money saved, because even with falling cell prices, the battery pack remains the most expensive component in most EVs. That brings us to the manufacturing-led design philosophy Tesla has been advertising for years: build the car with fewer parts. One of the most talked about examples is large single-piece castings, often called gigacastings, used to replace complex assemblies made from dozens of stamped components welded together. In traditional manufacturing, the rear underbody might involve many parts and many welds. A large casting can collapse that into one or a few pieces, which can reduce tooling, reduce welding robots, reduce time in the body shop, and reduce the number of quality checks needed to ensure every weld and seam lines up. When you scale that across hundreds of thousands of cars, minutes saved per unit become enormous capacity gains, and fewer operations generally means lower cost. But there's a real-world trade-off that comes with those big castings, and it's one buyers should pay attention to: repair economics. A multi-part welded structure can sometimes be repaired by replacing a smaller section. A large casting can, depending on the damage in the repair network, push repairs toward replacing bigger assemblies, which can increase costs for insurers and owners. Tesla and casting advocates argue repair procedures can evolve, sectioning techniques, improved parts availability, better diagnostics, and that the production savings still win overall. Critics argue the insurance math could be painful in some markets. If a next-gen compact Tesla does lean even harder into casting, watch how Tesla supports repair documentation, parts supply, and certified body shop capacity, because those factors can make the difference between cheaper to build and expensive to fix. Another major cost lever is something you won't notice on the street: how the car is assembled. Tesla has described a next-generation manufacturing approach, often summarized as modular or unboxed assembly, building major modules in parallel, then bringing them together later. Instead of a single long linear line where the car moves station to station, the factory can do more work at the same time. Front module here, rear module there, interior installed into a body section in parallel, then married together. The design of the vehicle has to support that. Mounting points, wiring routes, cooling lines, and structural interfaces have to be engineered for fast, repeatable joining. If it works, the payoff is huge: fewer steps, less conveyor space, lower capital cost per unit of production, and faster ramp. In other words, the design is not only what the car looks like, it's how well the car's architecture matches the factory's most efficient workflow. Paint is another outside-facing cost center, and it's a big one. Paint shops are expensive to build, expensive to operate, and slow compared to other parts of assembly. An affordable EV program often reduces paint complexity by limiting color choices and avoiding multi-layer specialty finishes that take longer and cost more. Design can support this by keeping panel shapes and gap strategies consistent across trims, reducing the number of exterior variations, fewer unique bumpers, fewer trim-specific add-ons, fewer wheel designs, fewer appearance packages. To a buyer, that can look like fewer customization options. To a manufacturer, it reduces part numbers, reduces inventory mistakes, reduces scheduling complexity. and increases the percentage of cars that can be produced in the most efficient mix. When the goal is mass market pricing, variety is often the enemy of scale. Then there's aerodynamics, which most people think of as a range conversation, but it's also a cost conversation. A slicker shape may allow a smaller battery for the same advertised range, and it can reduce road noise and improve highway efficiency. The cheapest mile of range is the mile you don't need to store in the battery. That's why you may see a next-gen compact Tesla prioritize a clean, rounded profile, careful management of airflow around wheels, a smooth underbody, and minimal exterior protrusions. Even things as mundane as mirror design, wheel arch shaping, and ride height tuning can add up. And again, the payoff isn't just better range. It can be same range, less battery, which is how you cut cost without advertising we gave you less. Now move to the battery, because if there is one place where an affordable Tesla must get the formula right, it's here. While Tesla uses multiple chemistries today, a lower-cost, high-volume compact would logically lean toward lithium iron phosphate, or LFP, because it typically avoids expensive nickel and cobalt and has a strong track record for durability and thermal stability. The trade-off is lower energy density, which can mean more weight for the same capacity, and potentially more difficulty delivering long range in a small package. But if the car is lighter and more aerodynamic, and if Tesla targets a realistic mass market range rather than an ultra-high number, the LFP equation can work. It's also a chemistry that can be charged to 100% more routinely, which can make a smaller pack feel less limiting day to day. The way the battery integrates into the vehicle can also cut cost. Tesla has been exploring structural integration, making the battery pack a more direct part of the car's structure. In manufacturing terms, that can reduce parts count, reduce the need for separate reinforcements, and save weight. In service terms, it can complicate certain repairs. But for a program designed around scale and speed of production, structural integration can be a major cost lever. It's the same theme repeated: fewer parts, fewer steps, fewer dollars. Let's go inside, because the interior is where cost-cutting becomes personal. People will accept smaller cars, they won't accept an interior that feels flimsy or annoying. Tesla's signature interior approach, minimal physical controls and a clean dashboard, has always been partly a design statement, but it also has a manufacturing advantage: fewer components. A traditional cockpit has a driver instrument cluster, a center infotainment screen, physical climate controls, switchgear, trim stacks, vents with complex ducting, and sometimes multiple control modules. If you consolidate functions into one central screen and simplify the trim and ducting, you reduce the number of unique parts, the number of fasteners, the number of wiring connections, and the time it takes to assemble and test. That's not just theory. In automotive manufacturing, seconds matter, and connectors, clips, and alignment steps are where time and quality issues accumulate. But minimalism has its own risk: usability. Drivers often want immediate access to basic functions like climate, defrost, wipers, and audio volume. If a cost-focused Tesla leans even harder into touchscreen control, the company will be betting that software design can overcome the lack of physical buttons. That means fast UI response, clear menus, and smart steering wheel controls. If the UI feels laggy or buried, the cost savings can show up as customer frustration. So watch the user interface as much as the materials. In a modern EV, the feel of the car is as much software as it is plastic and fabric. Seats are another area where savings can be large without being obvious. Seats are heavy, mechanically complex, and expensive, especially when you add power adjustments, heating, ventilation, memory functions, and premium upholstery. A value-oriented EV often reduces cost by simplifying seat frames, reducing the number of motors, limiting power functions on base trims, and using upholstery patterns that are durable and easy to manufacture. Even small decisions like one less adjustment motor or a simpler seat control module multiply into serious cost savings at high volume. The trick is avoiding the impression of a cheap seat. Shape, foam tuning, and fabric quality can create a good experience without luxury car complexity. Interior materials and trim strategy also matter. Cutting cost doesn't have to mean harsh plastics everywhere. It can mean fewer unique surfaces and fewer variants. A program built for scale tends to use repeatable materials, molded in color parts, and fewer stitched or multi-layer assemblies. Stitched dashboards look premium, but they add labor and variation. A simplified trim strategy can still look modern if the textures are well chosen and the panel fit is consistent. In fact, some of the biggest quality wins come from simplification, because fewer parts means fewer gaps to misalign and fewer squeaks and rattles to chase later. Another key inside the car cost decision is feature content. Audio systems, ambient lighting, center consoles, rear climate vents, and convenience hardware. For an affordable model, Tesla could choose either to delete hardware on base trims or to standardize hardware and differentiate features through software. Software-based differentiation can be profitable, but it doesn't always reduce cost unless it also reduces how many distinct hardware configurations the factory must support. If you build too many variations, you bring complexity back into the line. So the more likely cost-cutting path is fewer trims and fewer hardware combinations. That can disappoint buyers who want a very specific mix of options, but it's one of the fastest ways to reduce manufacturing chaos and raise throughput. Now let's talk about a hidden cost center that is becoming a headline issue in modern cars: wiring. Wiring harnesses are heavy, expensive, and labor-intensive. They also create quality risks because each connector and clip is another potential failure point. Tesla has signaled interest in moving beyond the traditional 12-volt electrical system toward 48-volt low-voltage architecture. Higher voltage at the same power means lower current, which means you can use thinner wires and less copper. Copper is expensive and heavy, and reducing it helps both cost and efficiency. The average buyer won't care whether the car is 12V or 48V, but they will care if it helps Tesla hit a lower price without sacrificing features. Along with 48V, there's the concept of zonal electronics. Instead of one big centralized wiring harness running everywhere, you place local controllers in different zones, front, cabin, rear, and connect them via a simpler backbone. This can significantly reduce harness length, reduce connector count, and make assembly easier, especially if the vehicle is built in modules. It can also simplify diagnostics and potentially improve reliability because there are fewer long wire runs and fewer complex junctions. Again, this is the kind of engineering that doesn't show up on a brochure, but it can be the difference between a car that's cheap enough to build profitably and one that needs constant incentives to move. Then there's the sensor and computing strategy, another area where costs can be shifted rather than simply reduced. Many automakers add expensive sensor suites with LiDAR and multiple radar units. Tesla has historically emphasized camera-based perception with heavy computing. The advantage is lower sensor hardware cost. The risk is higher dependency on software performance and validation. For a mass-market car, this is not just a tech debate, it's a cost debate. If you can deliver required safety performance with fewer expensive sensors, you can lower the bill of materials. But if software maturity or regulatory requirements push hardware additions later, costs can creep back in. This is why any next-gen Tesla will be closely watched not only for its price, but also for what it includes: cameras, radar decisions, compute hardware, and how Tesla positions driver assistance in the value segment. So what does all of this mean for the rumored 2026 compact Tesla in practical terms? The broad picture is that Tesla's cost reduction would likely come from a stack of strategies working together. A smaller and lighter vehicle aerodynamic efficiency that allows a smaller battery, simplified exterior options, fewer parts through casting and module consolidation, a factory process optimized for parallel assembly, an electrical architecture that cuts copper and labor, and an interior designed around fewer components and fewer variants. None of these alone guarantees an affordable EV, but combined, they attack the problem the way a manufacturing company would: reduce complexity, reduce time, reduce parts, reduce weight. And it's worth emphasizing, cheaper to build does not automatically
Looks like
mean
the
cheap
exhaust
to
mount
buy.
is worn.
Pricing depends
Okay,
on
mark it
demand,
for replacement.
competition,
Will
tariffs,
do.
incentives, battery material prices, and Tesla's own margin strategy. If the car is in high demand, Tesla could price it higher than enthusiasts expect. If competition is intense, especially from lower-cost global EV makers, Tesla may be forced to price aggressively. By 2026, the compact EV space is expected to be crowded, and cost discipline will matter for everyone, not just Tesla. We also need to talk about where cost-cutting can backfire because consumers will feel those consequences quickly. Repairability and insurance costs are one. If large castings and structural integration reduce manufacturing cost but lead to higher repair bills, the ownership cost can rise even if the purchase price falls. Interior usability is another. If minimalism becomes too minimal, and routine functions require too much screen interaction, buyers may reject it, especially in a budget segment where practicality matters. Feature expectations are another. If the base model deletes too many comfort items, like decent speakers, useful storage, or effective HVAC, buyers will compare it not to other Teslas, but to well-equipped gas cars and hybrids that still compete on convenience. And finally, real-world range, especially in cold weather and at highway speeds, has to match buyer expectations. A smaller pack can be fine if the car is efficient and charging is convenient, but if winter range drops hard or charging speeds aren't competitive, the value proposition weakens. So what should viewers watch for as Tesla's next-generation compact becomes clearer? First, factory clues. New line layouts, casting expansions, supplier announcements, and evidence that Tesla is truly building vehicles and major modules in parallel, rather than relying on a traditional long assembly line. Second, battery choices, chemistry, pack integration, and sourcing, because policy and incentive rules may reward localized supply chains in some markets. Third, electrical architecture, whether 48V and zonal wiring show up at scale, because that signals serious cost and complexity reduction rather than superficial trimming. And fourth, trim strategy. If Tesla limits options and standardizes hardware, that's often a sign the company is prioritizing manufacturing efficiency to hit a lower cost target. In the end, the most important takeaway is this: affordability in EVs is becoming a design problem as much as a battery problem. The next wave of cheaper EVs won't come just from one breakthrough in chemistry. It will come from rethinking the car as a product of the factory, designed to be assembled with fewer parts, fewer operations, less wiring, less weight, and less variation. If Tesla's rumored 2026 compact, whatever its final name, delivers on that philosophy, the biggest innovation may not be something you can point to on the dashboard. It may be the invisible engineering that makes the whole car cheaper to produce, inside and out, without looking or feeling like a budget car. That's the latest. If you want, I can rewrite this as a tighter broadcast script with time cues for a 22-minute package, including intro, field VO, 2 short interview placeholders, and a 30-second closing tag for the anchor.